Welcome to our APSC 459 final project presentation. My name is Ben Starkey and my group mates are Kucera, Eric Finlay, and our project is called The Grid. The Grid is a 3D volumetric LED display. The basic premise is to take a two-dimensional array of LEDs and spin it fast enough to produce a three-dimensional image. The basics of this project are based off the Revolver, a display produced by APSC Studios. We decided to improve on their design in several categories. Our original plan was to produce an image with 75 by 75 resolution, 4mm squared pixel size, 24 Hz frame rate, and 120 frames per revolution. We estimated their display to have 50 by 50 resolution, 7mm squared pixel size, and an unknown frame rate and 100 frames per revolution. We did not complete our original goals, but we made significant strides in all three main areas: software, mechanical, and electrical.
My name is Kucera and I'll be covering the software section. The software of this project was divided into two main objectives. The first objective involves transforming a 3D model into usable data, while the second objective involves writing the code to display this data on the LED board. The transformation from a 3D model into a usable form starts with the creation of the 3D model. The models used in this project were created with the free 3D model software Blender and exported in the DirectX file format. This format lists all the vertices and edges in plain text, making it much easier to parse. The program reads the information from the DirectX files and saves the model triangle makeup in a list, then creates a grid by layering 50 rays that are equally spaced and parallel to the XY axis, then 50 rays perpendicular to them. It will make a separate grid for every 3 degrees for 180 degrees to produce 60 ray grids. The program then iterates through all the triangles and checks them one by one against all the rays using a parametric ray triangle intersection algorithm. This process repeats for all the ray grids to create 60 2D cross sections. Once all the intersections have been determined, they are then outputted in two forms. The first is the form that would be inputted into display, which consists of 50 characters, either ones or zeros, depending on what the LEDs are on or off. There are 50 lines per cross-section and 60 cross-sections per model. The second output was a list of intersection points that could be fed into the display program. This program was written in MATLAB, and its purpose is to take the intersection points and plot them in 3D. This allows the user to see what the output would look like without having to upload and run them all on the display. The second objective, writing code for the display, is on hold until a prototype has been developed.
Hi, my name is Eric Finlay and I'll be talking about the electrical component of our project. The original electrical plan is as follows. There will be three main components: the motor, the LED grid, and the LED control systems. The motor is going to be powered by a 12-volt laptop power adapter. The speed is going to be controlled by a half H-bridge. It is unclear at this time whether the motor will be controlled by an encoder or held steady at a pre-specified speed. The LED grid will be composed of either 3 25 by 75 grids or 9 25 by 25 grids. Experimentation is ongoing to decide which LED to use. Once the decision on which LEDs used has been made, traces of the grids can be planned. The LED control system is the most complicated part. The output of the ray triangle intersection algorithm will be loaded onto the apparatus using an SD card reader. This data will be interpreted by an Atmega 328 chip. The chip will control a series of serial in, parallel out shift registers. The rows will be cycled through sequentially, while the columns will be serially loaded and outputted in parallel to correspond with the row currently powered. We attempted to keep all sections fairly modular to allow for fixes and upgrades. Our prototyping had a couple of goals. The first was to determine the shortest pulse that would produce visible light in an LED. Using a phototransistor, it was determined that we could detect pulses on timescales as low as 3 microseconds. From these tests, it became apparent that some LEDs had undesirable transient behavior. Due to these observations, tests are currently underway to confirm which LEDs would be appropriate for the purposes of this project. To get proof of concept, we constructed a rig to spin some LEDs on a lathe. Using this rig, it was determined that pulses of 5 microseconds are capable of producing visible light. Furthermore, we determined that a 300 microsecond gap between pulses is sufficient to produce 2 distinct points of light. This was essential information since the limits of our system mean we must flash one frame every 328 microseconds to get 120 frames per rotation at 24 Hz. This video shows that we can set up 10 distinct points when rotating at 1500 RPM, and this video shows we can get 120 distinct points at 1500 RPM.
My name is Ben Starkey and I will be explaining the mechanical portion of this project. In this section, I will be discussing the similarities and differences between our project and the APSC Revolver, which the project is modeled from. I will also go over the basic layout of our design. APSC's design used a large, possibly 13-inch diameter plastic tube and put their entire circuit board inside the tube. For our project, we are not going to use one massive circuit board due to manufacturing difficulties and costs. We are also not going to use the large plastic tube because it's approximately $900 to purchase. For our design, we decided to use I-beams to connect the top and bottom discs. There will be a lattice between the two I-beams which we will attach all circuit boards to. We have decided to place the assembly between two of the main support pillars in order to get a larger, unobstructed 180-degree viewing angle. When the final unit is constructed, there will be a 1/16 inch polycarbonate sheet bolted to each face of the unit. In order to spin the assembly, a pulley system will be used which will be powered by a DC motor. There will be two shafts, one on the top and one on the bottom. Each shaft will be press fit to one of the discs. The top and bottom shaft mounts will be slightly different. The top shaft will only have a radial bearing, whereas the bottom will have a thrust bearing and a radial bearing. The shafts will be placed into a block of aluminum which will have two concentric holes drilled into it. The first will be the deepest hole and the smallest diameter. The thrust bearing will sit in this hole. The second hole drilled will have the diameter of the radial bearing. The radial bearing will press fit into the end of the bottom shaft and top shaft. On the bottom, the inner ring of the radial bearing will come into contact with the top ring of the thrust bearing, thereby taking the weight of the assembly. This can be seen in the picture shown here. The I-beam assembly will be built and tested on the lathe between the 18th and 25th of this month in order to determine if the amount that the design will vibrate is acceptable. 3 pieces will be built: the bottom disc, which will connect to the chuck of the lathe, 2 I-beams to connect the top and bottom discs. The top disc will connect to the tailstock of the lathe. This assembly will be spun at 1500 RPM on the lathe, and accelerometers will be attached to the lathe in order to measure the vibrations caused. As a control, the lathe will be spun at 1500 RPM without the proposed assembly, and data will be taken. We will then look at the difference between the two measurements. If the vibrations are substantial, research will be made to see if counterweights can be installed to improve balancing. If this is too difficult to accomplish, we will look into design alternatives.
We would like to thank the Engineering Physics Project Lab, Dr. John DeCane, Christopher Waltham, and Bernhard Zender. Thank you.